In this talk, I'll be giving you some tips, some tricks, and some tools regarding Flutter performance. You've probably heard this line before: Flutter is fast by default and you do not need to worry about performance. While this is true for the most part, and it is important for me to note that you should not be pre-optimizing any of your apps when not needed, but understanding what can cause your app to be slow, and more importantly, how Flutter's rendering works underneath the widgets that you use, will level you up as a Flutter dev. A quick intro: my name is Gordon, I work at Stream as a Flutter Developer Advocate, and I also have a YouTube channel called Fun with Flutter that, you guessed it, covers Flutter topics. I hope you learn a few valuable things from this talk, because I've wasted so much time in the past not using the correct tool for the job. So let's get started. But hold on, we don't have that much time and there's a lot to talk about. So before we can actually get to the fun stuff, we need to have a lower level fundamental understanding of Flutter first. So don't leave. I know this looks boring, but I promise that this talk will get a lot more interesting. I'm actually going to go over the fundamentals quite fast, as later on we'll take a more practical look at everything discussed in the following slides. So first, let's take a look at all the different phases that are responsible for rendering. We can see that we have the build, layout, and paint phase. And then finally, all of this creates a display list that then will then be rasterized by the GPU. So the GPU will display it as an image that can be rendered to the screen. The build phase is what we as Flutter developers are responsible for. This is the rendering phase that we control the most, as this is where our widgets get rebuilt and the subsequent elements for those widgets get inflated. And from those widgets, we also create the relevant render objects. Then we head into the layout and paint phase, and the framework or render objects manages this, and we generally do not need to worry about layout and painting. You have the option to create your own render objects, of course, or you can always manage custom painting through a custom painter. We'll explore this more in upcoming slides and what to consider performance-wise. So let's break these phases into the well-known Flutter trees. There are 3 trees: the widget, element, and render tree. And we will use a simple example to illustrate how these trees work together. Here we have a widget called myWidget that returns a red container. And as you can see, Flutter builds out our tree. The interesting bit at this point is that there is another widget added automatically. This widget is called a colored box. In the build method of the container above it, it is determined that the colored box is the appropriate widget to return, as all we are doing is setting a color in the container. In the element tree, you will note that we have a component element and a render object element. Rather than creating the render object directly, a component element creates render objects indirectly by creating other elements. And a render object element has an associated render object widget in the render tree, which handles concrete operations like laying out, painting, and hit testing. Important to note, our widget tree actually does not care about parent and child relationships. The element tree manages that. A widget is purely just a piece of configuration that is used by the elements and the render objects. And then finally, we have our rendered colored box in the render tree, the only thing in our render tree at the moment. Flutter created everything to the left to finally have this one render object. And this is the core of the rendering library. This class implements the basic layout and painting protocols. Okay, so really interesting, but why should we care about any of this? Well, let's take a step back and only look at the widget tree. Here we see something we are familiar with, a stateless widget. The stateless widgets are the myWidget and the container widget. But what is this render object widget? Well, the render object element uses the render object widget for its configuration. What this means is that this is a widget that will be rendered to the screen and not just the component element or component that lays out other widgets. These two methods, create render object and the update render objects, are two methods on render object widget that can create and update a render object. Whether the widget creates or updates a render object is determined by the associated elements. Here, Flutter tries to be smart about updating render objects whenever possible instead of recreating them. This is very important. This is an important topic to understand when it comes to Flutter being fast, while also being easy to use. And just like we have a stateless widget, we also have a stateless element. An important thing to note here is that if we change my widget to now be a stateful widget, the state will be kept by the stateful element between widget rebuilds. The widget tree will be destroyed and recreated a lot in a normal Flutter app. For the render object widget, Flutter creates a single child render object element, and yeah, that's a mouthful, but the name says it all. There are also a multi-child render object element for more than one child, for example, a column widget, and a leaf child render object when there are no children, for example, an image widget or a text widget. Let's go back to our example. We'll change my widget to now be a stateful widget instead, and then add a gesture detector. When clicked, it calls the method changeColor, which sets the state and changes the color from red to blue. The darker nodes are those that were added or changed. As you can see, the trees are starting to grow, and it's already getting complicated. The question now, though, is what happens when we tap the gesture detector? How does Flutter efficiently change the color of the container without doing any unnecessary work? This is where the whole concept of these different trees come into play, the reason why we have these abstractions. The widget tree is designed to be torn down and recreated a lot. Widgets are meant to be lightweight blueprints used by the elements and render objects. While widgets can be recreated a lot, the associated elements and render objects are reused as much as possible. To put it more simply, widgets are immutable and elements and render objects are mutable. Something that is extremely important to take note of, though, is that the fact that Flutter can determine what element and render objects it can and can't reuse by checking to make sure that the type of the widget has not changed. For example, if we rebuild the entire widget tree, and all we change in the tree is my widget with some other widget. For example, a widget called exact same different name. Then that will cause Flutter to recreate all of the elements and render objects for that part of the tree, even though all of the widgets lower in the tree are still the exact same. Keys in any form helps the Flutter framework to match widgets with the correct elements and render objects. So this can help alleviate some of the problems we just saw. For example, if you have multiple widgets in a column with the exact same state, then keys help Flutter keep track of which widget has which state. If you need more control over when Flutter reuses render objects, for example, when you move widgets higher up or lower down in the tree, then you can take a look at global keys. Unfortunately, we don't have enough time in this talk to cover it in more detail. That said, we did it. We got through the theory. Now let's actually get to the fun part and explore the tools and the examples. And the best way to understand Flutter is to explore the underlying code. This is the best tool to your disposal, the fact that Flutter is open source. You can read and change the platform code. In Visual Studio Code, you can also enable these two settings to allow you to add breakpoints and debug the underlying SDK. You can do something similar in Android Studio. For our first demo, we'll take a look at the container with the color example that we've been using thus far. And this demo will showcase the base tool that you have, your IDE. So just a recap, this is the code that we'll look into. The container with a set-state call to change the color. Using our IDE, we will set a breakpoint on the updateChild method that is on the element class from the Flutter framework library. This method is what gets called for each widget's element to update the render object with the new widget information. We're going to go over this fast, and it's not too important to understand everything, and I will also give simplified info for everything on screen. In the update child, Flutter does a lot of things. One of those is also calling updates on the child and passing in the new widget configuration. And in update, we pass in the render object widget to super.update, and we also set locally the child. Then in that super.update method, Flutter again does a lot. What we care about is the call to update render object on the widget, where we also pass in the render object. And then in the update render object, all we do in this scenario is update the color of the render colored box, which is the render object. And as you can see, there is a set method where we set the color. This method has a check to make sure that the value has actually changed. If the value is the same, then the method returns. Otherwise, it calls mark needs paint. And this is the main takeaway. Flutter tries to be smart about only updating what and when it is needed. If we proceed to take a look at mark needs paint, you can see it looks quite complex. All you need to know is that it tells Flutter that this render object needs repainting. Something that is interesting though is that we can also check to see if this render object has a parent in the render tree. If it does, then it marks that parent as also needing repainting. This is interesting and something we will explore more later on. I definitely encourage you to play around with this in your own time. Look at the code, like the underlying Flutter code, and see what is happening to your widgets, the elements, and your render objects for yourself. Next up, let's explore the build phase a bit more. And by a bit, I actually mean quite a lot. Flutter recreates widgets a lot, and that generally doesn't matter too much. I'm putting generally in air quotes. We still need to be careful, and we shouldn't be needlessly rebuilding widgets, as it requires Flutter to unnecessarily check to see whether the matching render object needs updating. We don't want to waste any computing, especially not when we are animating. To explore that, let's take a look at a tool that allows us to track widget rebuilds. The Track Widget Rebuilds option in IntelliJ and Android Studio allows you to do as the name says. As you can see, when we call setState, it rebuilds my widget and all of the widgets in that build method. This tool is particularly helpful when you're doing animations or working with lists or anything more complicated than a simple example. You may have a bug in your code that's rebuilding widgets when certain state changes, when it's not at all needed for those widgets to rebuild. 10 out of 10 recommended tool. Actually, all of the tools are 10 out of 10, so we can get that out of the way. Next up is the profiling timeline in DevTools. We can use the timeline in DevTools to identify unnecessary rebuilds, but that's not what this is truly useful for. This timeline is meant to identify frames in your application that are expensive to compute. But if you enable enhanced tracing and track widget builds, then you will see all of the widget build methods that were invoked for each frame. Important to note that the time it takes to complete a frame is important. If it takes too long, then that will cause jank in your application. The red frames you can see at the top left indicate jank in the timeline. So jank, if you're a gamer, this will be more familiar to you. It means that the application drops frames and causes a stutter. Drop too many and it becomes noticeable and people will complain. So Flutter aims for 60 frames per second, and that is considered good for mobile. Your eyes won't be able to noticeably pick up a delay between frames. Normally Flutter does 60 FPS without any issues, except when it doesn't. If we go back to our previous example of the different rendering phases, we can actually take note which is the UI thread and which is the raster thread. And you'll note that these match up nicely with what we see on the timeline. The general rule is that if the UI thread is slow, then you made a boo-boo somewhere in your widgets or state handling. This is code that you wrote and code executed by Flutter's framework on your app's behalf. The UI thread creates a layer tree, which is basically a series of painting commands, and sends the layer tree to the raster thread to be rendered on the device. The raster thread takes the layer tree and displays it by talking to the GPU. If the raster thread is slow, then it can unfortunately mean a lot of different things. Most likely you still made a boo-boo somewhere, or you're trying to do something too graphically complex, or you're trying to do something that Flutter is just not great at handling. We'll cover all of these later on. Flutter uses Skia for its graphical rendering, and we will also take a deeper look at Skia in the upcoming slides. You can easily see an overview of your app's performance by enabling the performance overlay. For this overlay to work, however, you need a material app widget in the tree. This will show you a real-time view of the device, of how long each frame takes. So you can use your application and identify areas that cause jank. While we are talking about different threads, it's worth mentioning isolates. And isolates are like threads or processes, but each isolate has its own memory and a single thread running an event loop. Every isolate has its own memory heap as well, ensuring that none of the states in an isolate is accessible from any other isolate. When using isolates, your Dart code can perform multiple independent tasks at once, using additional processor cores if they're available. Unfortunately, we don't have time to delve deeper into this topic, but if you're doing any long-running operation in your Dart code, then it could be a good candidate for isolates. Dart also has recently released something called isolate groups that enable you to spawn multiple isolates that live in the same group. Isolate groups enable performance optimizations such as sharing code. I recommend this video on the topic if you're interested to learn more. There are also 3 different Flutter build modes. Debug is the first one. A number of dev tools only work in debug mode. It's also what allows hot reload and restart. Then we have profile mode to get an indication of your app's performance, but this still being able to do a performance profile. So sorry, what I mean to say is that you're still able to do a performance profile in release mode. You're still able to do a performance profile in profile mode. And then finally, we have the release mode. This is used for when you want to release your beautiful app. The architecture between debug and profile or a release build is completely different. Dart does a lot of optimizations for a release and a profile build. For example, tree shaking, null safety, and removing unneeded code and checks and so forth. Release mode should be the fastest, as most of the tracing is also then removed. If you want to go beyond just seeing what widgets get rebuilt and repainted, and you want to analyze how long the build times of each frame and widget is, then you will need to run in profile mode. You can only run in profile mode on a real device, meaning an emulator won't work, and even if it did, it would not be indicative of what the performance is like on a real device. Okay, we've explored quite a bit. Now the real question is, how do we reduce widget build cost? The big question, the money question. The first thing you should always do is make use of constant widgets whenever possible. We can talk quite a bit about the benefit of const. A const variable is a compile time constant, which means a single const object will be created and reused no matter how many times the constant expressions are evaluated. For widgets, this means that Flutter won't unnecessarily rebuild widgets marked as const. Flutter will be smart about determining that the widget's build will not have changed, so it can sometimes skip rebuilding it. To get this compile time optimization, we will actually need to build for profile or release mode. You can explore this yourself, but when we call setState, Flutter is smart enough to not rebuild the const widgets if not needed. This doesn't apply for widgets though. This doesn't just apply for widgets, it also applies for any object. In this example, we have a for loop iterating from 0 to 100, and we're creating an object called const object and a const object not. One is constant and the other is not. I apologize about the naming. As you can see, if we inspect our memory, we have a single instance of the const object and 100 of const object not. So always prefer const when you can. Let the tool do the heavy lifting and determine what should be marked as constant or not. I recommend using the default lints from the Flutter Lints package. All new Flutter projects use these by default. Or if you use custom linting rules, be sure to do proper lints to prefer constants. When it makes sense, you can also use static or non-constant objects. You can use static for non-constant objects, I should rather say. When the class can't be constant, but you only need a single instance between all of your projects, for example. Both of these classes are not constants, and we create 100 instances of the const object not class. Inside that class, we create a static final of const object another not, and inside the constructor, we print that static object. This will create 100 const object not instances, but only a single const object another not. I'm sorry about the naming. You can also be clever in the way that you do your execution. If it's not necessary to compute something, then don't. Let's take a look at an example. In this example, we have a simple condition and two expensive operations. If the condition is true, only then will we call the first expensive operation, and only if that is also true will we call the second. If the first condition was false, we will never call the expensive operations, and as a result, we saved on our compute cost. We can also sometimes increase the readability by using the late keyword. This example is exactly the same as before, but take note that operation 1 and operation 2 will only call the expensive operations once we try to access them, because of the late keyword. This is referred to as lazy computation. A big shout out to Remy for inspiring this example. Also a big shout out for him for a lot of the topics that we will talk about in the following slide. Definitely follow Remy on Twitter. I have personally learned a lot from him. Back to widgets. The next important thing to reduce our widget build cost is to prefer small widgets. The main benefit is that it reduces the widgets that need to rebuild when calling setState. It also makes testing a lot easier. Here we have the good old counter example. When you press the floating action button, it calls setState, which causes all of the widgets in my homepage to rebuild, except for those that are constant. Can you think of a better way to do this to avoid all these widgets rebuilding unnecessarily? You guessed it, state management. The state management frameworks we have are amazing, and all of them have their own ways to reduce widget rebuilds in your application. My personal favorite is Riverport, and you can get very clever with Riverport and how to optimize your application. But we're not going to argue about our favorite state management solution. We'll keep it simple. Back to the counter example. Let's unnecessarily optimize this like the developers we are. As you can see, we're using a plain old value notifier and value listenable builder. Now only the floating action button and the text will rebuild when the button is pressed. There are many other ways we could have done this as well. Was this necessary? Definitely not. We basically overcomplicated and overthought something that didn't need to have been. But the principles remain. And it's always important to keep your widget rebuilds in mind. And it also doesn't hurt to have the extra performance. It may come in handy for complicated logic in the future. So next up, what should you prefer? Creating widgets or creating helper methods? I'll give you some time to look at the code and to give your opinion in the comments. If we just quickly look at the code, it seems like using helper methods would be the faster approach. But there is actually no competition. We've indirectly touched on some of the points why you should prefer dedicated widgets. But yeah, the main reason is that when we call setState or when we rebuild a particular widget, we want to contain that to only rebuild what is needed. This becomes really hard to do with helper methods because our builds become really big, and as a result, just because of a result of using helper methods. If you want more information on this, this is a great video on the topic. So we've covered quite a bit regarding widgets, but this is the last thing, and this is probably the most important. Don't do expensive work inside your build. It's the fundamental thing you should probably take from this talk. There's a lot of optimization we can do across our Flutter apps, but this is something you should be mindful of from day one. It's a lot harder to later refactor code that does a lot of work in the build method. We've seen and talked about the fact that widgets are just blueprints for render objects and that Flutter recreates them a lot. So keep them small and lightweight. In this example, we are removing the call to really expensive operation from outside the build to inside the state class, as we now know the stateful widgets is managed by their elements, meaning we can be smart about taking expensive work out from the build and putting them in our state instead. And Flutter can recreate the widget as much as it wants. However, if the widget is removed from the widget tree, the associated elements and render objects will also be removed, meaning you could lose the state and cause it to later be recreated once the widget is added back to the tree. So the question is there a better option? You can put it in the comments if you want to. The answer again is state management. So we can abstract complicated logic out from your widgets to your state management of choice, and be sure to reuse as much logic and not redo any work when not necessary. Okay, we can finally move on to the next section. Now let's move on to another area of the rendering phase, and that's something that you can also help to control, the paint phase. As we've talked about before, a widget's painting is managed by the associated render object. You normally do not have to think about this step at all, but when should you think about it? Well, basically when you notice a lot of painting operations in your timeline, or when you notice it takes up a lot of time. You can enable track paints in enhanced tracking for more information, and you can also use the CPU profiler to see if you spend a lot of time calling paint, for example. Let's take a look at a more practical example. We have our normal My widget that we've used before, but now it's sitting in a stack on top of a custom paint that paints something called Expensive Painter. As you can see, it is a rather complex painting. Intuitively, you might think that Flutter paints this Expensive Painter once and only repaints My widget when it updates. And actually, no, it does not. When we did our debugging earlier, we actually saw that the child would call its parent as well, and that would result in my app rebuild or repainting in its entirety. In this video, you'll see that even though only the My widget is being updated, the entire stack is being repainted, and the reason for that is because Flutter repaints everything on screen each frame unless you tell it not to. You can also see that both the UI and the raster thread are working really hard. Note that this is on a profile release on a real device. We can easily solve this by introducing something that's called a repaint boundary. This widget creates a separate display list for its child, which can improve performance if the subtree repaints at different times than the surrounding parts of the tree. A render object will repaint whenever any render object that shares the same layer is marked as being dirty and needing repaint. With the repaint boundary now, you'll see that in our paint phase, we are only repainting the colored box and not the expensive painter. Also, after a couple frames, the engine decides that it's worth it to cache the image, and subsequent raster thread frames complete faster. The dark red bar in the third frame actually indicates the compilation time. So we should put a repaint boundary around everything, right? Not really. A repaint boundary basically instructs Flutter to cache the image. Raster cache entries are expensive to construct and takes up a lot of GPU memory, so only cache images when necessary. And that said, the engine may anyway ignore a repaint boundary if it thinks it's not useful. You can also see some metrics on your repaint boundary. In this example, it says that it's an outstandingly useful repaint boundary. You can also see which images are being cached by enabling the checkerboard raster cache images flag. So if we run the app and look for images rendered with a randomly colored checkerboard, this indicates that the image is being cached. The checkerboard images should remain constant. You don't want to see flickering, which would indicate that the cached images are being recached. I made a long video about this if you want to explore this topic in deeper detail. The next tool, Highlight Repaints. This is a fantastic tool to easily observe repaints in your application. This will basically show you the different repaint boundaries in your app. Fun fact, Flutter automatically adds repaint boundaries to items in a list. When you highlight the repaints, you can see the different repaint boundaries. If you were to add something to the bottom of the list, none of these render objects will repaint. Using this tool helps us at Stream to observe a weird behavior in Stream Chat Flutter, where if the list is in reverse order and new items are added to the top, then everything repaints. The elements and render objects are recreated, which means you also lose access to these states. There's a way that you can help Flutter to determine the new positions of items in a list so that it doesn't need to repaint the widget. As you can see here, the colors stay consistent when a new message is added at the bottom. And again, we made a long video for this, well, not too long, talking about this on our Stream Developer channel, showing how we optimized our list views. We don't have enough time to cover this in more detail though. Back to our container example. Let's take a look at the following code. What do you think will be the output? What color do you expect? And again, I'll give you a few seconds to type the answer in the chat. Okay, correct. Everyone that got it correct, the answer is red. Let's actually delve deeper into what is happening at the Skia painting level. To illustrate the painting instructions that we sent to Skia, we will run our application in profile mode and then use the Flutter screenshot command to capture a Skia screenshot. Then we'll go to the Skia debugger and load the file that the previous command generated. At debugger.skia.org, I'll load the Skia file and then we will inspect the instructions. This is what happens in the raster thread where Skia runs. As you can see, we create our red container with the draw rect instructions. Now back to our example, let's change it a bit. We'll add another container, this time a blue one above the red container. So again, in the chat, tell us what color will it be now? I'll give you a few seconds. And correct, it is still red. So congratulations to anyone that got correct. But if we take a look at the painting instructions in Skia, you can see that we still go through the process of painting the blue rectangle. Flutter and Skia is unfortunately not that smart to optimize that out on our behalf. So something to keep in mind when you do more complex painting. There may be times when it makes sense to not render something when something else obscures it. Given that that something is complex to render. This blue container is very simple and won't have an impact. So back to our code. We'll make it a bit more complicated and add an opacity widget with an opacity of 0.5 between the two containers. And again, what color will it be? You have a few seconds. Correct. It's 8B6C94 in hex. Congratulations to everyone that got it correct. So I promise there is a point to this. Let's load these instructions into the Skia debugger. As you can see, there's quite a few more instructions. Most notably is this call to save layer. This bad boy is something we should pay attention to, at least according to smarter people than myself. Calling save layer allocates an off-screen buffer. Drawing content into the off-screen buffer might trigger render target switches that are particularly slow in older GPUs. So basically that means that you should try to avoid it when you can. There are a few things that could cause a call to save layer, and generally some rules you need to think about. Use opacity only when necessary. Clipping can cause save layer when using a clip behavior of clip anti-alias with save layer. And other type of clipping is not as expensive as opacity, but it is still costly. I suggest reading the documentation for up-to-date information and more info in general. Okay, so you're telling me I can't use opacity and clipping. No, don't worry. There's 100% of the time, 80% of the time a way around it. Back to our example, let's modify it slightly. We remove the opacity widget and instead set the opacity in the color. As you can see now, the call to save layer has been removed and order has been restored. So let's take a bit more practical approach and look at a real world example. I made a demo application using the StreamChat SDK to create a sample chat app. But this one is a bit special. It also uses Rive to allow you to send animated stickers, and it also has animated reactions. The important effect that I want you to take note of is this blur effect that is applied when you long press on a message. If you're interested in any of this, we have a code lab that walks you through it step by step. It's showing you exactly how to create this app. So checkerboard off-screen layer. This is a switch you can enable in your application to check whether your app is using save layer. Once this switch is enabled, run your app and look for any images that are outlined with a flickering box. The box flickers from frame to frame if a new frame is being rendered. Now in this video, we will turn on checkerboard off-screen layer to true, and as we navigate in the app, you will see randomly colored checkerboards wherever we do more complicated effects. This is a nice switch to turn on to identify areas in your application that are calling save layer, and it may prompt you to do further investigation. However, just because it is showing doesn't necessarily mean it's bad, it just means you need to be mindful. The effects that you decide to use or not is dependent on the product and the design. In this example, it is doing quite a bit, blurring the underlying Rive animations. If all of this is not enough, then you can run in profile mode with the trace skia flag. This will give you a more detailed look at the raster thread and what skia is doing. An interesting tool is the more debug options that you can only run in debug mode. This allows you to disable certain effects in your application so that you can easily see if it has an impact on performance. I believe this is a fairly new tool. I personally haven't used it much, but it looks really interesting. Another awesome tool in DevTools is the highlight oversized images. This tool will invert images that are too big and that are using too much memory for the size they're taking up on screen. These images I'm using in this example should be replaced with smaller images. And okay, previously I mentioned that clipping can also be costly, but luckily we can also try to be smart. Here we are using clip-rect to do the clipping. This will clip all of the children, and this can be expensive. Depending on what you want to do, you can maybe simplify it. Instead of using clip-rect, make use of the border radius that is available on a lot of widgets. This won't always be exactly what you need, but when you have the option and it works, use it instead of clipping higher up in the tree. In this scenario, it produces the exact same results and is less complex. This could make a big difference in a large application with a lot of clipping. I strongly recommend that you read the docs for all of these components that we are talking about. They are updated frequently with the best practices, and the clipping docs, for example, give a lot of useful information. Okay, let's continue to look at another example. If you want to apply opacity to an image, then rather than setting the color directly, rather than using opacity, you can set the color directly and use a blend mode. And when we want to animate opacity, instead of manually animating the opacity through set state or some other technique, use fade transition instead. There's also lots of built-in optimization in the fade transition class. Some other gotchas. These are all things that might cause a call to save layer and are potentially costly, so use with care. All of this that we talked about is nice to know, but that doesn't mean you shouldn't use any of these widgets. Just be mindful not to overuse them, especially not in animation or lists or wherever it's happening a lot. Or maybe you have an alternative to one of the widgets mentioned previously, a way to do something more optimally. Okay, next up, the power of caching and reusing widgets. Animator Builder is a good example of caching widgets. Here we create the child once and then reuse it in the builder. In a similar way, you can cache your own widgets and use builders creatively. Finally, if you ever notice that your animations jank the first time you run them, but not for later runs, then that could mean you will benefit from precompiling shaders for your application. This is quite easy to do. However, as a topic, it is quite dense to cover. DevTools will give you a warning when it detects a frame that will benefit from pre-compilation. I recommend reading up more about this on Flutter's website. This has previously been a big problem on iOS when they switched to Metal for graphical computation. But that said, Flutter and Dart is always improving, so this and a lot of other things mentioned in this talk may be less of a headache in the future. So, what's next? Unfortunately, a lot. There was a ton we could not cover in this talk, and even more that I don't know about or that I don't yet understand myself. But there's a lot of great information out there. I don't need to do an introduction for Philip. He's made fantastic blog posts and videos on Flutter performance. If you want extra information, you can watch or read any of those. Or you can take a look at the interesting work the Flutter team and community is doing with regards to performance optimization. Explore the open issues and see what people are discussing and what they're working on. And that's it. It was a lot. I hope you found this talk useful. Please ask any questions and I'll try my best to answer.